Suppose R is a relation from A to B and S is a relation from B to C. In part A, we want to prove that the domain of S composed with R is a subset of the domain of R. Let's draw a picture of this. We have three sets A, B, and C, where R is a relation from A to B and S is a relation from B to C. And okay, an element of the left side here, the domain of S composed with R. Well, S composed with R is a relation from A to C. And so an element A in the set A would be in the domain of S composed with R if we can find an element C and C over here such that that ordered pair is in S composed with R. Okay? And so suppose that's the case, then we're supposed to show that A is in the domain of R. Of R. And that's true because if this is in the composition S composed with R, then that means there exists some B in the set B such that AB is in R and BC is in S. Okay, so because AB is in R, that means that A is in the domain of R. And so that's the idea. Let's write it down. We have R and S being relations, and that's our goal. And first we write the definition of subset, and then we let A be arbitrary and do direct proof. And now we have elements of the domain, and so we use the definition of domain, that there exists some C such that AC is in that composition, in that relation. And same thing over here, but R is a relation from A to B, and so I'm going to use the letter B to denote the second coordinate this time. And then we can do existential instantiation to get a C naught, for which that statement is true. And okay, what does it mean for A C naught to be in that composition? Well, definition is there exists a B such that AB is in R and B C naught is in S. Okay. And then from there, we can do another existential instantiation to get that statement for B naught. And we don't really need both of these statements, right? We only need the first one. So we have A B naught in R, and that proves that there exists such a B, right? The B is B naught. Okay. So let's write up this proof. I already written here, let A be arbitrary, and in fact let it be an arbitrary element of domain of S composed with R. So we are bringing that over here for direct proof. New goal that A is in domain of R. And then we did existential instantiation, right? To we use a definition of domain, and then we eventually ended up right here with this statement about C naught. So we should say there exists some C naught in C such that A C naught is in the composition of S and R. Okay, and then the fact that it's in the composition gave us this as the definition, and then existential instantiation got us to down here. Right. So we can say it follows from this being in the composition that there exists some B naught in B such that A B naught is in R and B naught C naught is in S. Oh, forgot a parenthesis. And then we decided we only cared about the first half of that, which was this, and that gave us what we wanted. Okay. So, because I'm only using half of what I just stated, I'm going to say in particular, it follows that A is in domain of R, right? There exists such a B, and that was the definition of A in domain of R. So that finishes part A. Now for part B, we're going to prove that if the range of R is a subset of the domain of S, then this thing we proved earlier, the subset statement is actually an equality. Okay, so I mean, we've already proved that the left side is a subset of the right side, so all that's left is to prove the right side is a subset of the left side. Let's try and see if we can illustrate why that should be the case. All right, so suppose we have an element of domain of R. So that would be some A for which the ordered pair AB is contained in R, right? And then we want to show that that's in the domain of S composed with R, right? Which is a relation from A to C. And so we need to find an element C in the set C such that AC is in S composed with R, all right? And I mean, if we had sort of some element of S here, which was B with something else, then we could just compose those two and find what we need, okay? And the assumption here, that's not true in general. There might not be anything in S that starts with B. But with this assumption that the range of R is a subset of the domain of S, there has to be, right? Because B is in the range of R because this ordered pair is in R. And therefore, it's also in the domain of S. And that means that there exists some ordered pair BC in the relation S. And once we have these, we can put them together to get, by definition of composition, that we have the ordered pair AC in the relation S composed with R. Okay, so that's the idea of how the proof's going to work. Let's put it down in a table here. We have our same assumptions as last time, and we have the thing we proved in part A, right? And then we have I'm already doing direct proof here. I'm taking this antecedent and moving it over as a given, and our consequent becomes our goal. Okay. Now, often when we're proving an equality, we've said, well, for all x, x is in the left side if and only if it's in the right side. Okay. This time I'm using the other sort of way of proving an equality of sets, which is to show that each side is a subset of the other side. I'm doing that because I've already, in part A, proven one of those, one half of that, so that'll be convenient. All right. So yeah, so there's the one we've already proven. So it just remains to show that domain of R is a subset of domain of S composed with R. And from this given here, we use definition of subset to get that statement. And similarly, definition of subset with our goal gives us this. And I've used B over here because I'm talking about something in the range of R, which is the set capital B, so that makes sense. I'm using letter A here because I'm talking about something in the domain of R, which would be in the set capital A. All right, so we'll let A be arbitrary and do direct proof to get a new given of A in domain R. And then the definition of that is that there exists some B such that AB is in R. And definition over here, there exists some C such that AC is in S composed with R. And again, I'm using C here because S composed with R is a relation from the set capital A to the set capital C. So something in well, something's in the domain if and only if there's a second coordinate C, and that would be in the set capital C. All right. And then from there, we have existential instantiation. Gives us the first thing here, A, B naught in R. And then actually from that, it then follows that B naught is in the range of R, right? Because it's the second coordinate of some element of R. Okay. Now the reason I wanted to get that was so I could do modus ponens with this guy right here. So we can do universal instantiation first, and then modus ponens. Well, okay. We're going to get to that in a moment, I guess. This is just definition of AC being in the composition, right? We have a B in the middle such that AB is in R and BC is in S. And now we do modus ponens to get that B naught is in the domain of S, which means that we have a C in, such that B naught C is in S, and then one more existential instantiation gives us B naught, C naught, and S. And all right, now we're trying to prove this monster over here. And which value of C are we going to prove that for? Well, probably C naught, and the value of B we're going to prove it for is B naught. And so we get that statement as our particular goal. And we have it, bringing down that from above. Those two pieces give us our goal. Okay? Boy, that seemed a lot easier when I drew the picture. Let's type out the proof. Let me bring up what I have so far. I've already done the direct proof step. So suppose range R is a subset of domain of S. We show that these two sets are equal. And then we have already shown this statement, which gives us the first half of our goal. So it remains to show this one, right? And for that, we let the definition and then let A be arbitrary. And in fact, an arbitrary element of domain of R, right? We're going to show that A is in domain of S composed with R. Great, so that's our new goal. Now, the first thing was to use A in domain of R to get this definition, which gave us a B naught such that A B naught was in R. So I will say there exists some B naught in B such that A B naught is in R. And then right after that, we went ahead and said that, okay, well, if that's in R, that means that B naught has to be in the range of R. So it follows that B naught is in the range of R. Great, okay. And now the next thing after that was, what did we do? Well, we did modus ponens, right, with these two to get that B naught is then in the domain of S. And this conditional here came from here, which originally came from right here, right? This was the definition of range of R being in domain of S. So that's what we want to talk about in our proof. Go back to the set theory statement and stay away from these arrows, right? Keep the logical notation out of the proof. So we will say because range of R is a subset of the domain of S, and because of what I wrote in the previous line that B naught is in range of R, we have that B naught is in the domain of S. Okay, good. And that means that there exists some C such that this is an S, and then when we just do our instantiation, we get this. Okay. So therefore, right, because B naught is in domain of S, there exists some C naught in C, oops, such that B naught C naught is in S. Okay, and now we put it together, right? We take that together with A B naught in R, which we had from up above, which we've already mentioned in our proof, right there. And together those give us that well, let's see, that if we have that these two are both in there, then well, that tells us that A C naught is in S composed with R, right? There exists a C, in particular C naught. Okay, so we'll say because A B naught is in R and B naught C naught is in S, it follows that A C naught is in S composed with R. Okay? And because that's in there, we have our goal that A is in the domain of S composed with R, because A shows up as the first coordinate in some element of S composed with R. So therefore, A is in domain of S composed with R. And that finishes the proof. All right. Now you may well decide that when you do your existential instantiations, you do not want to add a subscript 0 on everything, and that would be quite reasonable actually. So if you are ready to take that sort of stylistic step, then that is fine. Your proof will come out just the same. You just have to remember that when you do that, you're sort of changing a bound variable into a free variable. Okay.